This is based on two papers, one at NeurIPS last year and the other at CEPR this year, both led by Litu Raut. He's sitting somewhere in the back. And in collaboration, several people, both in this room and outside. In this room, it's Negin Rauf. She's sitting right here. Yanis, who's somewhere around here, Yanis Daras. And my colleagues, Konstantin Karamanis and Alex Demarkis. And folks at Google Research, part of the Pixel team, Yujia Chen and Vincent Chu, and also with DeepMind, Abhishek Kumar. With that, I'd like to get going. So the problem is the following. Okay, I want to solve general inverse problems for images, meaning I have a ground truth image, for example, this dog. I've got a camera system. Maybe the camera is moving. Okay, so it's motion distortion. There's some noise added. And so these are measurements I get, this image on the other side. And what I want to do is to start from the image and reconstruct what the original thing is. This is an age-old problem, such reconstructions. Many decades, and there are I'm studied across various communities, including image and signal processing, for decades. So I'm not going to talk about the entire history of this problem, but talk about the more recent machine learning history and what people have been doing recently. The difficulty for these problems is that it's ill-posed, meaning given this image, there could be, it's not clear that this is the only image that's consistent with these measurements. There are potentially infinitely many solutions. So what you'd like to, one approach is to use prior knowledge of how natural images should look like to try to find a likely image that is consistent with this measurement. So this is generally the goal of inverse problems. So there are many types of inverse problems. Here are various examples. One is something called freeform inpainting, meaning I delete part of the image here and I want to reconstruct it. And this is one possible reconstruction. There are other reconstructions as well, but this is just one possible one. This is a motion deblur. So I've got this, and I want to deblur it to get back to this dog. Or a super resolution, in which case the image is pixelated as in this one, and I want to sort of unpixelate it. So this is another inverse problem. Or some foggy thing, Gaussian deblur. I want to get things back. So these are all examples of inverse problems in images. And of course, there are many other domains in which inverse problems make sense. For example, John Temer here has been working on MRI type inverse problems, very different set. But today I'm not going to talk about anything else, just these kinds of inverse problems. So one standard solution would be supervised methods, which is, I take an image which is clean, I distort it. In this case, say I box in paint it, take some other image, create, distort it in some way, create pairs of images, one distorted and one clean, and train a neural network to reconstruct it, a supervised model in a sense. Okay? So this is going to depend on the data set, this type, and the type of the type of distortion. Or if I want to deal with motion deblur, then I would create a different data set and train a different model. So for every type of data set and for every type of distortion model, I would create a model. And these things work very well. But what the more modern take on this over the last, I would say, decade are unsupervised methods, where you'd essentially like a single model to deal with various types of distortions and solve all these things using the same pre-trained generative model. So I'm going to talk about these unsupervised methods. Essentially, they use the following box. You have a box which can generate images from the distribution of images. So what do I mean by that? So look at this image. It's a 512 by 512 image in RGB, which means it's a vector. If I just vectorize this whole thing, it's a vector in about 800,000 dimensions, 512 times 512 times 3. Okay? So from now on, for me, image equals vector of 512 of this incredibly large dimension. So all I want is to sample such a, but not all vectors in this large dimensional images. Most are junk, just noise. Okay? So what I want is a distribution. I want a box that can sample from quote unquote natural images in this very high dimension. Or I just want a sampler P of X. So if I have such a box, then how can I use it to solve these kinds of inverse problems? That's really what I'm driving towards. Why do I want to use this roadmap? Because now there are generative foundation models such as Stable Diffusion, Imagine, and DALI, which are really good at this sampling problem. Meaning, give me an image from the set of natural images. They've been trained on internet scale data. Somebody has spent a lot of money on computation, collecting the data as well as compute to actually create these models. And so what we'd like to do is to use somebody else's work, these models, and try to solve our problem. So in terms of generative models, which is sampling from these distributions, the recent history starts from various autoencoders, GANs, and more recently, a series of works on diffusion models, which are now the state of the art. Some of the landmark papers in this are Sol Dickinson et al., Song and Herman, and others which are listed here. So they're today the state of the art for these kinds of generators. So I want to spend a few minutes talking about generation using diffusion models and then move to inverse problems. Okay. So roughly, what is a diffusion model? Well, a diffusion model is just a Markov chain-based sampler. For those who haven't seen a Markov chain-based sampler, all it means is the following. A state in this context of image is just a gigantic vector, or if you want to imagine, a possible image. Okay. At each time, this is a giant state machine with random transitions. That's what a Markov chain is. And from any state, you can move to some other state. And eventually, as this state machine is evolving, and I run it for a large enough amount of time and stop it, the sample I should get is an image. It ends up in a state which is a natural image. That's all you mean by a sampler. Okay? All right. So what do I want to do? I want to start with something which is easy to generate, just a random noise. And I want to run this Markov chain such that eventually I get this nice image. Okay? Right now, I'm not even thinking about solving inverse problems. I'm just talking about generating an image. So a diffusion model is essentially such an object. You can start from pure noise and try to get good images. The question is, what are the transitions looking like? Typically, each step, what you have to do is some amount of noise and some amount of drift. All this means is, if I'm in some vector, how do I go to the next vector? That's the drift. And the noise says, well, I don't want to deterministically go to the next place. I need to sort of jitter it a little bit. Okay. So this transition is known as, to do this, you need something called the score function. So again, there's a lot of equations here. Given that there's a 20-minute talk or 25-minute talk, I'm going to skip all the equations and just talk through sort of what is going on. Okay. So to do this, the way you do this roughly is the following. Start from a clean image, noise it till you get your sequentially noise it. So it's a little bit noise, a little bit more noise, a little bit more noise, and get to pure noise. And then figure out in each reverse step how to denoise just a little bit to go from this to this. If you can figure that out, then you can patch them all together to run the sampler which I want. And it turns out you can do this inverse problem. You can't learn essentially through this score function. I'm not going to get into it. And that's really how diffusion models work. Okay. All right. So suppose I have this box that can sample from the natural images. The question is then, how can I solve inverse problems using that? What do I mean by that again? I have an image, a true image, but I have a noisy version of it, a distorted version of it. I want to now find a true image that is consistent with this distorted image. So the variable I want to deal with is y. Always, I have the minimum number of variables in my talk. Y is simply the measurements. So what I want is an image consistent with y. Okay? Instead of just the previous problem was give me an image. Now I'm asking give me an image that's consistent with y. Formally, then, what I want is I don't want to just diffuse to get any image. I want it consistent with the known measurements. Essentially, I want to deal with a conditional distribution. I want to sample from the conditional distribution of images given the measurements y. That's all I want. And the machinery which we talked about previously directly applies to this. Instead of sort of diffusing with the usual score, I need to deal with something called the conditional score. That is given you want something which is consistent with whatever I know about the image. All right. The problem is, of course, I don't have access to this conditional score. I have access to the usual score, but sort of standard probability, you can decompose this. You can use something called Bayes' rule and decompose it into two parts. The two parts roughly mean the following. When I take every step back from a noisy image to a less noisy image, okay, the direction in which I should go should depend on sort of how images look like, which is sort of what score function is capturing. And the second thing is this following term, which says, if I had this particular noisy image right now, that's xt. Think of xt as the current noisy image. Is it consistent with the measurements I have right now? And if it isn't, how do I align things right? So I need these two things. I need to take two different scores and push it forward. The second one, unfortunately, is unknown. I don't know how the measurements would look if the noisy image is given. So let's dig into this a little bit more. Okay, let's look at this. So I have this noisy image, and I want to know how measurements would have looked like in this case. What I do have is the following. Suppose I give you this pure image, this true image. Then can you tell me how the measurements would look like? The answer is yes, because I know what the camera system is. If I give you this image, I can send it through my model of my camera system and tell you why the measurements would have looked like. So an approximation that people have done, this is the diffusion posterior sampling paper, is the following. Hey, I have this image. Try to estimate what the clean image would look like. Take that estimate of the clean image, figure out what would be the measurements, do this approximation, and then I can figure out roughly what my correction turns should be in my drift. Okay. So summary is that I have my noisy image at some point. I need to figure out how to move forward. Well, I'll take the noisy image, estimate a clean image, take the estimated clean image, look at what the measurements would have been associated with it, make the error, and use that to guide my diffusion. Okay. Yes, Jay.
So if you have like inpainting or some linear math and you know the measurement, then you don't need that.
You do. So if you have the clean image, then you have the measurement map. This is exactly what you're asking. We can figure this out. What I'm dealing with, what?
Yeah, if I'm doing inpainting.
Okay, when I say noisy image, I don't mean noise because of the measurement system here. This is the noise introduced when I'm diffusing through the thing. Remember, I'm starting from pure noise. There's nothing to do with my camera system. I'm moving along in the space of images. I've gotten certain non-image yet, but partial image, which is what I'm calling a noisy image. I want to start from that. I want to figure out what the image associated with that is. Suppose there's a way to predict this in some way. Then I can apply to this exactly what you said, the camera system, get my Y, and figure out what the conditional score. But what I have actually is only this. I want to figure out directly from this what my measurement would have been. So I can do an approximation, which is given mean square, some estimate of this, an expected value of this, and then apply that. So this is essentially an approximation. And it turns out this approximation is essentially equivalent to an exchange of an expectation and a function. Okay. You want to compute the average of something. Instead, you take that something and put in the average. That's what mathematically is happening here. But this leads to bias. Yes. Yes, there is. And that's all I was trying. A longer version of this talk would actually tell you exactly what it is, what the error is, and all that stuff. There's an approximation, but there's an exact. He asked, is there a closed form expression? The answer is there is.
Because the exactness is hard. Yeah,
I can write the exact in terms of an integral, which is an expectation, it's a conditional expectation. And so you can write it as an expectation of some quantity which I haven't even set up the notation for. And then the approximation is equivalent to change the function and the expectation. That's what it formally is.
But there is a new result that I think Price has, I don't know if I can see it, that says that if you wanted to compute the conditional score, there is some hardness statement that
absolutely. There are distributions. So in general, doing this exact or arbitrary distributions is hard. Is a recent there's lower bounds recently with Aditya Parulekar, Eric Price, and others. Good. But right now, I'm just talking about this particular approximation. This is the DPS approximation. Okay. What's the problem with this? Well, this seems to work well. This was state of the art as of last year was this approximation. There are two issues with this. One is that you're working completely in image space. So every time you change the image data set, you need to do this whole business. You need to retrain this again. And when you go out of distribution, there's problems. And second, of course, is there's this approximation of an exchange of expectation and function. And what it qualitatively leads to, this exchange of expectation and function, is blurry images and fine details. Okay. That's what it qualitatively leads to. This actually goes back to something Alex and others have worked in the past. If you take if you average if you've got a system with many possible solutions and you average them, you'll get blur. Okay, that's roughly what, and you can see that when this is another instantiation of that kind of an issue. Okay, so we want to fix this. We want to take care of these two issues. One is I don't want to work in 800,000 dimensions. I want to work in much lower dimensions. And two, I want to somehow correct this error between exchanging an expectation and function. All right. So the first part, this is one attempt at solving this kind of a problem, this first paper. I'll talk about a second way in about 5 minutes from now. This is based on joint work with several people in this room. As I mentioned earlier, and it is at NeurIPS last year. So the obvious thing to do here would be saying, okay, take somebody else, you've got stable diffusion. That gives you an encoder and decoder for images. So let's do diffusion in the latent space instead of in the pixel space. So instead of working in 800,000 dimensions here, you take the encoder and go down to about 12,000 dimensions. So that's the order of the latent space of stable diffusion. Still large, but much smaller. And then you can do exactly. So what do? You start from random noise. You find score functions, so-called in the latent space. Stable diffusion already gives you the score functions there. You diffuse it through and get the image. So this was generation. But I want to solve conditional generation. So what I need to do is exactly what we talked about previously, which is given a noisy latent vector of an image, I need to make that consistent with the measurements. Okay. So what the natural way of doing what we did previously would be the following. Whatever vector you have, predict what the clean latent vector is, decode it, apply the look at the measurements associated with it, and then figure out how to drift down here. So you're working in two spaces. You predict, use the decoder, and then figure out what the drift is in latent space and move it forward. Okay, you can make this formal, and you can get an exact expression for this thing only if encoder and decoder are one-to-one maps, but they are not. Okay, and it does, and because of that, you realize that there is some, again, it leads to blurry images. This works reasonably, but it gives again some blurry images. There's a second, so you can say, okay, let me try to fix it in a different way. The way I could fix it is the fix focuses on the following observation: that hey, if I have a quote unquote good latent vector Z, which actually corresponds to the image as opposed to some arbitrary latent vector, if I decode it and encode it, I should get back the same thing. Okay, and so this gives me a fixed point I can try to go towards. So what do? Well, I'm at some noisy latent vector. I estimate what should be the clean latent vector, decode it to get what I think should be the image. But then I have a measurement already telling me something which is true about the image. So I'll just patch those two together. Essentially, I'll glue what I know on what I don't know, I'll keep from the prediction. What I do know, I'll just glue it on and then encode it back to get a latent vector. And once I have that, I can try to sort of regularize it such that this Z hat T, which is what I think should be the latent vector, is consistent with what I predict is the latent vector. It's a certain regularizer which you're forcing, which is trying to deblur things. Okay? And this regularizer, we can show some pseudo theory with this for for sort of linear systems.
We call it pseudo theory. Yeah.
And we can show it recovers, it's a fixed point, it's an attractor and all that. But more interesting is, it was, as of last December, the state of the art in terms of how you could solve these kinds of inverse problems. Okay, in terms of quality, the image quality. So these are all images from the wild. Here, this is for example, if you look at the top line, we blocked out the head of this person, and this is the ground truth. The second one, so two state-of-the-art commercial methods we have shown here. This is what our method generated. And if you look again, the fine details are better, and numerically also this is better in terms of various usual scores that this community looks at. Here's another example. There's a hugging face demo where you could sort of delete some of the, you could take an image, you can upload the image, you can erase parts of it and ask it to regenerate. And this is what PSLD, which was this algorithm, did this regularizer. Good. So, but let's step back and ask what we did. I told that there's a problem, there's a exchange of an expectation and a function. That was really the problem which is leading to the bias. The way we fixed it is not to address it, but just throw on the regularizer on the side and saying that hopefully that will work. Okay. Seems to help better. but can you actually just attack the problem head on? So going back to your question, yeah, you can write the exact expression and you can write the expression. But instead, what you can do is write the exact expression and use a Taylor series expansion of that function. Okay? And then truncate it at the second order term instead of just you can show that it's for any exchange of an expectation on a function is essentially a first order Taylor's approximation. It's exactly the same thing. So you can say, hey, let me look at a second order Taylor's approximation of this, which will lead to a second order score is needed. Some Hessian score is needed to do this kind of a thing. Okay. And it turns out there are ways of estimating this Hessian score as well. But the sample complexity of this is much, much larger. Okay. That's really the problem. So all this is known. It's really the sample complexity, which is really large. And the dimension D is about 12,000. I'm trying to estimate second order scores. I'm trying to learn D square quantity or D cube quantity, which is just there's no point. It's almost impossible to do this in practice. Okay. So really the contribution of the second algorithm, again, I have 5 minutes. Okay. The contribution of the second algorithm, I'm not going to go into the details, is the following. We compute we write this and find a lower bound, a surrogate loss function. The important thing about the surrogate loss function is that you don't need to know the Hessian, you just need to know the trace of the Hessian. Okay, for diffusing in the surrogate loss. If you want the trace of the surrogate, okay, there are standard ways of estimating trace of the Hessian through random projections. For example, if a matrix is A, then if G is a random Gaussian matrix, expected value of G transpose AG is the trace of A. Okay? This is a Hutchinson's estimator, which essentially leads to a new algorithm, which is doing a 2-time scale thing. You are doing a diffusion in latent space, moving from one step to another. And within each step of the diffusion, you're running a stochastic approximation based on random projections. Okay. It is correcting the drift locally and iteratively. And this has some, the formal property is this a lower bound. The second statement you can make is if the underlying, if the true distribution was Gaussian, we can say something a little bit more and so on. But formally, in general, what we have is surrogate loss, which is looking at second order terms. And because of that, the hope is the image quality will be much better. So this is practically implementable because we are only running very, very small number of stochastic approximation steps. Because we are essentially integrating over time. That's sort of what stochastic approximation does anyway. And it's essentially 3 times faster than sort of previous state of the art methods. So, and you don't need a new state. You don't need to compute second order score functions. You don't need retraining and trying to compute new second order score functions and so on, because all we are looking for is trace of these things, which can be estimated using random projections. So let me talk about some image results, and then I'll talk about numbers in a second. Okay. This is really what I want. So my point was earlier, if you remember, exchanging an expectation of function is actually averaging should lead to blurring. So let's see what happens. So this is a ground truth. If you look at that sort of the macro scale, all these dogs look reasonable. They're all good, reasonable dogs. But let's look at the eye. So I want you to focus on this little box on the top. Okay. So this is the true image. This box. This is the input we are given, which is a blurred image. So all methods, including our previous method, the eye has lost a lot of detail. Whereas the newest method is actually able to, because of the second order correction, you are able to recover much more fine detail, which is really the takeaway of this. Okay. And I can show you other images as well. But in terms of numbers, in terms of scores, it's LPIC score or PSN, it is the state of the art. And more importantly, in terms of computation, an advantage of doing the second order correction. So how do you deal with first order? We know that there's a bias in the previous methods. So the way you deal with bias is to take large number of small steps. Okay. So typically you would run 1,000 steps of diffusion to actually deal with the fact that you are having a bias drift all the time. Okay. So instead now, because we are doing a second order correction, it suffices to run only 50 steps of diffusion. Of course, each step of diffusion is more expensive because locally you're running a stochastic approximation. And so yeah, essentially what you should see is how many times are you calling the score network and NFEs, neural function evaluations. And effectively, our method uses 250 steps compared to some of the previous methods, which was even including our own work, which was about 1,000 steps. So you're getting a fourfold reduction, and the image quality is better. So this is work, as I said, in collaboration with the Google folks, and we are sort of transitioning this to products, as it were, at this point. Once you have the second order correction, you can do other interesting things. You can start doing text guided editing. So I have about 3 minutes, Alex. Perfect. So the general inverse problem is taking this noisy image and giving a clean image. Okay. But if I also add the word face associated with it, I'm getting similar images. But now if I say face with red hair, then essentially, I can give this. The conditioning I'm doing is not just y, which is a measurement, but y comma z, where z is something else, which is some clip encoding of this text. And I want to generate images consistent with multiple things, and such things are possible. So these examples are taken, this is well known, and these examples are taken from 2 papers, the NTI paper by Muqtadi et al. And Direct by Kim et al. Okay? And in fact, as they point out, again, this is not our work, the T-Reg paper, they point out text regularization does something else as well. So give a noisy image and ask you to generate clean images without text regularization, and you run it multiple times. You look at these 4 bears, they're all blurry, and each time it will get different ones. Whereas if I put bear, it's giving some more information, which can sort of ground it better. And if the quality of the image increased better. And formally, what they've shown is that, hey, let's look at this particular axis here and look at the variability of this across these images. Text regularization reduces ambiguity. Okay? So it's good. So what you want is text guided things for various reasons. So what does STSL do in that sense? So I don't have time to get into the methods, but text regularization, these kinds of the previous methods require essentially in the latent space some ground, a baseline, a clean, a noised version of what the clean image would look like inside their algorithm. And what we can do is actually now produce such things very easily using STSL. I'm not going to get into the details of that. And a result of that is the following. If I give a noisy input of this tiger and give it the text prompt, a tiger walking in the jungle to a leopard walking in the jungle. Okay, this is what the previous state of the art was doing. The reason the problem the previous methods were not working very well is this is not a noiseless image of a tiger. It's a very noisy image of a tiger walking in the jungle. So what you need to do is simultaneously denoise as well as text regularize, and this is what our method is doing here. Okay. Another example, this is a car in front of a house, and we want to convert it to a bicycle in front of the house. So I want the same house. A previous method may change the house, whereas our method is actually able to get similar kind of house with the bicycle in front of it. So this text regularized things. And we can deal with both corrupted and clean images with the text prompt. I'm not talking about the methods. It's what we talked about used in a different pipeline. Or it even works with sort of inconsistent text. So you give this image input and say a high quality photo of a tiger, I want to convert it to a high quality picture of a leopard. So this is not a high quality image of a tiger. It's actually a low quality image of a tiger. So it's inconsistent text, but STSL can deal with that and gives you sort of clean images of leopards. So this is where we are at. So the summary is that what I've talked about is sort of inverse problem for images, and also how you can do sort of principled correction of the drift field, which will lead to sort of various benefits. We are continuing. There are many more steps you can go with this, and I'm happy to chat about that offline. Thank you.